If you would allow me to introduce you tonight.
Go for it.
I've known Ben for a really, really long time, but I'm going to kind of stick to the script here. So tonight, Ben will be talking on heavy timber trusses. And Ben is, of course, a principal at Fire Tower Engineered Timber. And Ben is the co-founder of Fire Tower Engineered Timber and he has more than 40 years of experience in timber framing, including extensive research on mortise and timber joinery. Ben holds a degree from Cornell University. He holds one from Colorado State University, and he holds his PhD from Stanford University, where I met him. After a stint as professor at the University of Connecticut, Ben ran off and joined a circus at Benson Woodworking, where he toiled to help build that company, our industry, and the guild. And I don't think I'm overstating that. So after 20 years, he left to found one of the premier heavy timber engineering firms in North America, where he now brings his considerable design skills, engineering brilliance, and deep understanding of timber framing and timber framers to bear on the engineering he performs. As you all know, that's why we hit 100. Ben is a gifted and engaging speaker, and it's a special treat for me to be able to introduce him tonight and to bring him as part of the TFGLive series to you this evening. So Ben, without any further ado, I am going to turn it over to you.
Thank you, Mac. And thank you all for being here. When Mac cajoled me into doing this, he assured me it'd be easy, and I thought it would be easy because I've spoken about timber trusses many times. I gave a 24-hour session on heavy timber trusses to the Montana Civil Instructional Engineering Association. And I thought, I'll just grab one of those. But it turns out my attention span's too short, and I was getting bored just looking at those old truss things. So about half of what you're seeing, I've never shown before. Every single slide has been messed with. And I thank you for joining me. And speaking of messing with them, I wouldn't be here and I wouldn't have done this unless Janet Kane had agreed to serve as the analyst in the background here. And I don't know if you know Janet Kane, but she's another structural engineer who specializes in timber structures. And she's a fine engineer. She's a great cook, an extraordinary gardener. And gosh, I'm proud to say that we're going steady. So here you go. Here I am. In the early 70s, going astray, becoming a budding truss whisperer. As I built this model, I turned to my left. I can still see this model. What is this? Almost 50 years later, I'm looking at that same model. I actually cut my fingers in the power saw building that model. That's why I've got them stuck behind me. We used the model to demonstrate, and here I am in 1973, reinforcing a 100-foot long covered bridge in north central PA, still there. In Pennsylvania, when you needed a 100-foot long bottom cord, you didn't just go cut down a 150-foot tall tree like you can in Oregon. So you had to splice the timbers for the bottom cord. And if all of structures is challenging of making connections that are sound, it's particularly true in timber, and it's particularly true of tension connections. So in this instance, these cords were all completely sound. There was no rot. They were well protected and covered, but at the lap splices they had, many of them had sheared. So rather than replace and dismantle this whole bridge, we just simply reinforced them with these diodag threaded high tension rods, and both inside and out of all four of both cords. So 4 sets of rods running from panel point to panel point to panel point, covered it back up, and now you'd have to be a troll to see what we did. So there I was getting started. Here I am. And this is the talk we're going to talk. This is what we're talking about tonight. Heavy timber trusses. Let's define them. If they're not 20 foot or 20 foot long, I'm really not interested at all. And you're more likely, given the size timbers that people seem to use in trusses these days, you probably got a beam really anyway at less than 20 feet. If you're buying commodity timbers, lumber, this 4x stuff, well, that's certainly a truss, and we'll show you an example or two using it. But most of the time, we're talking about heavier timbers than that. I believe that most trusses, certainly in timber, get very efficient only when you're above a 5/12 pitch. If you're less than that, what's happening is you're generating an awful lot of compression in the top cord, an awful lot of tension in the bottom cord, leaving you with a brutal connection to deal with. And the other thing you're dealing with is usually you've got a lot of short diagonals if you're trying to do diagonals to fill in that triangle. And that's very pricey and inefficient. And some of them are in tension and really tough to coordinate and to detail. So that in general, if we're below 512, I look for other solutions like keyed beams and big beams and things like that. And then of course they're exposed. I'm only in this because I love to look at what we build. All you people build beautiful stuff. I've gotten to design and build beautiful stuff. I want to see it, so it's exposed. Very few of them are hidden, the ones that I've been dealing with, although I do a lot of church work, reinforcing, repairing churches. So we're going to do this. We're going to use an example, and we're going to compare the ideal truss and the real trusses that all of us build here. And we're going to do a king post and a scissors truss and compare the various things that happen when you change loading and change dimensions and change pitches. Then we'll talk about connection methods. We'll talk about pegged mortise and tenons, not for very much. I'll show you a couple good ones, a couple bad ones. I'm really going to spend time on notches because it's your go-to joinery in trusses, I'm convinced, for changing tension, for exchanging big compression into big tension in the intersecting members. Nothing's more efficient than notch. We'll talk about rods, which are great in tension. We'll talk about screws, which are, I've used them in trusses, but mostly to sort of secure it and hold it together while I've also reinforced it. And you'll see examples of that. And straps, similarly. And then we'll talk about side plates. And I'm not going to say a lot of nice things about side plates, but I'll do what I can. But I'll warn you about the side plate trauma. And then we'll talk about a few wild trusses. So what about an ideal truss versus a real truss? An ideal truss is all the members, if you're talking about a truss, all the members are simply axial members. There's no eccentricities of the joint. All they feel is axial compression or tension, and they meet and end at every time the joint, when you connect them, all the members end at that joint. And it's usually a pinned, friction-free joint. We'll talk about that. On the other hand, our real trusses, a lot of times it's very bad to have all your member axes intersect at a spot. It makes the joint needlessly tough and you're unduly weakening your support, the member that's catching the other diagonals. So a lot of times we use eccentricity to good effect, but it is not the ideal. And most of the time we'll see at least continuous top chords or rafters, I'll hear them called. So you have continuous members, which are not the ideal. I'm not saying ideal as in platonic. I'm saying that this is the simplest model. Joinery, our joinery that we use can carry, depending on how we frame it, we can carry all sorts of moments and shears inadvertently or on purpose. And if you use the side plates, this is where you really get wrong, where you can really get yourself in trouble. Because instead of a small friction-free pin joint, what you've gone to is this big plate, which the plate can be big compared to the trusses and the members, and they can transmit all sorts of moments and shears that you didn't see coming, and you're not going to detail for it correctly, and you're going to get in trouble. We also describe our members as weightless. Obviously, nobody's doing weightless members except the SketchUp. I said everything stands up as SketchUp so far. When SketchUp starts getting gravity mode, I'm probably out of work. And then finally, classic truss analysis assumes all that the loads are applied only at joints, not in the middle of members. That's the only way you can keep them purely axial members, is to apply only at joints. We violate that almost all the time, but I'm going to show you what happens when you do distribute loads in various ways. So let's look at some trusses. This is an ancient truss, probably somewhere in England. This is a Janet Kane slide. I'm speaking the thing's just barely a truss. I mean, it's got a big triangle, so sure, that's trussy. These don't meet together in a triangle. There's sort of frame. We'll see these again. But more than anything, we also have a strut that looks like it's been there for a long time. So this is probably as much a structural handrail or a top plate of the transverse wall. But the location of these diagonals can play a crucial role in how forces are transferred throughout the truss. So let's look at this. This recently came in. This is one of our members. He's a longtime member of the guild and the former president. And I'm not going to mention his name, but Scott Murray might be on the phone, on the call. And he sends this, and he sends this to us knowing full well this is not an idealized truss, but it sells. And so who can argue with what sells? So he wants us to engineer this for what sells. And I tell him, hey, Scott, this is inefficient. He said, I understand. Shut up and do it. I said, fine, Scott, here we go. So what happens when you put the struts perpendicular to the rafter, not at the midpoint, you put them at the rafter, you leave a longer span down here than up here. And what happens when you separate them from the middle? You got a king post on king rod, unlike on the previous one. You have a king rod here to handle the tension imparted by the compression in these struts, but you've got a lot of shear in this bottom chord. As a matter of fact, for this to work, he sells them at 8x16, so that's good in Canada and Ontario, and that's great. They do need 8x14, and because of the increased bending on this side versus that side, we needed 8x12s for the same loading. On the other hand, just for interests and giggles, I said, well, what happens if you did this? If you flattened out the diagonals So they are basically the roof pitch. So they come down here, they take off the shear in the bottom chord, and they support the top chord evenly. What happens? Well, all of a sudden, because of the more even bending in the top on the top chord, they can go from 8x12 to 8x10. And the bottom chord, without all that shear, and it really is just in a tension member, and it can go from 8x16 to 8x10. Big change just by a modest tweak. And all I did was flatten out the pitch. Okay, so you bought 2 feet longer diagonals. You can send me the bill. So here you are. This is a big impact and shows you how the orientation of the members really matters a great deal. So this is what I would call an ideal king post truss. Some of the things that are going on is this a 12-12 pitch, but that's also a 45-degree brace. So the brace is parallel to this, which means when it comes off pretty close to the bottom of the king post, it hits the top chord roughly in the mid-span. You'll also notice it does hit the king post, and we're going to talk about this in a second. It doesn't hit down in here, which would be a concentric, non-eccentric connection, but it would also mean that I'd be shoving the bottom chord off the end of the king post, and I would have to detail this. And sometimes you see big through tenons in here and straps around the outside and all sorts of stuff to hold this a lot of tension between here and here. It's only because sometimes people will put these diagonals down in this crotch here, and that shoves this bottom chord off there, and you have to detail accordingly. Or you can go with fairly simple joinery if you keep it up here. Once you've said that, well, gosh, you know, once we're going to get the tension, or we're going to get the bending out of that bottom chord, then you could actually just go to a simple rod across here. And this is another slide from Janet. This is a rod because all it is really doing is the tension of the king post upper part of this frame. And I would point out this frame is really an interesting frame. This is a rod. You got to keep it in tension, and we'll talk about that. You have to either use a flat pitch, so there's a lot of force in this rod, and it doesn't get reversed by wind loads going across the top of it or by earthquakes shaking it up and down. This cannot handle any compression. It's only a tension member. Or you can put a lot of heavy load on it. We'll talk about one where we did that. I love this frame because it's called dogleg framing. This is what I call dogleg. This is a moment frame, a link of a rafter, a post, and a long brace, imparting lateral stability to this frame. This is a dogleg, meets a king post truss, and not only that, it does it with floating posts. Notice how they floated the posts off the walls. We don't need no stinking posts on the walls. We get them out here free. The kids can run around behind them. You can put bookshelves and all sorts of stuff out here. It leaves you room for a really great joint here. Instead of having to cut this rafter off right where there's a lot of prying induced by this brace, rather than having to cut this off because it ran into a wall, I can keep going over. All of a sudden, this joint is ever so much stronger now because I've got decent end grain on the rafter. So if you really take this to the extreme, we don't even need to connect the king post to the bottom chord at all. How bold is this? And I looked around, I've seen the slide somewhere in like Macedonia or someplace from 4,000 years ago. And somebody did it and got away with it for a couple thousand years. I could not find the slide, so I had to use this one. But that just goes to show you, if you detail this diagonal right, hit the king post and keep it in parallel with the roof pitches, there is really no tension here unless you start hanging heavy objects. If you start hanging heavy objects off here and swings, lights and stuff like that, then you better detail that for some tension, because that's a long span as a beam. It's fine as a tension member, but it's a long span if it's a beam. So now we're going to get into comparing various, and this is where Janet really kicked in. So we're going to talk about detailing trusses and what are the impacts on the force transfers among. So we're going to stick with a 36 wide. Trusses are getting interesting at 36, 12-foot bay, pretty classic, 9/12 pitch, 15 pounds dead load over the slope. We'll show you that. 16 pounds side load distributed. We'll show you that, but it's completely secondary. I'm really here for the gravity loads. Then we'll talk about snow load. I just picked a nice 40, or actually Janet picked a nice 40, but what we're really going to be looking at are the different ways that you can apply the load to these trusses. A lot of us use common purlins between these things at 4-foot centers. We'll show what happens. Some of us just put up heavy, thick boards or 12-inch sips that can span from truss to truss across that 12 feet. Heavy decking can do it. Some people put lumber, you know, 2x6s or 2x10s or 2x8s, I guess I'd use there. 2x8s at 12, 16 inch on center. We can also use the boards and panels. We can also load up with principal purlins. This is the Industrial Revolution solution. We'll run principal purlins between the king post trusses and a ridge, and then we'll put common rafters on top of that, which is my favorite roof. This is the richest of all roof ceiling plans. Who's scribbling on my slide? That's pretty cute. Is that me? And this is what they did. This is what the classic. This is the classic, is to load up the trusses at the points. And then there's finally just supporting it with a ridge. It has a huge impact. It looks like the same truss. It is the same truss. It looks like the same roof. It is the same roof, but it isn't loading the truss the same way. So here's the classic king post. We're leaving the braces in, even though they're probably as much trouble as they are good. But there it is. We're going to have 8x12 top cord. We didn't quite match the pitch, but close with 50 foot or 50 degree. It's not a 45. There's your diagonal. Notice I downsize them so that this is not a flush joint and this is not a flush joint. I like to do that a lot. Sometimes I'll even make this an 8x10 spun the other way so that you're looking at the 8-inch face, so this bumps into that. There's lots of games that I play to avoid flush joints which don't hold up very well. But we're going to see dead load distributed over the timber. We're going to see snow load distributed as it was if we're on the ground but hitting a roof, and then we'll look at wind load, which we're doing the simplest of wind loads, just a projected area above half point of the wall. So let's see what happens. So this is if you use classic purlins. You'll see if the purlin's on 4-foot centers, even one down in here. See, this is about half of it because this is 4 feet, so only 2 feet of it goes onto this, goes directly into the post. This is a little bit less up at the king post, up at the ridge, because these two are a little closer than 4 feet to the peak. So the spacing isn't perfect, but you'll notice that most of these are small 2.5 kip loads. And what we need in order to have the top cord handle this is an 8x14 top cord to handle bending and axial compression, the combined stresses in this cord. We need an 8x14, we need an 8x10 down here, an 8x10 for the king post. Notice that the king post has 9 kips of tension. What's that from? I got 7 kips in the diagonal propping the sag out of that top cord, 7 kips in this diagonal propping the sag out of the top cord. Those are in compression, propping the top cords up, pushing down on the king post. So these rafters, these top cords have got to hold that king post up with 9.3 kips. And we'll talk about that joint eventually. What about that joint? We're holding that king post up with this rafter. And then the bottom cord needs to be an 8x10. So there you are. That's classic. Pay attention to this. The top cord has 20 kips of compression. The bottom cord has 15 kips of tension. 20 kips of compression in the top, 15 kips of tension in the bottom. So this is one I've wondered about this and finally talked Janet into doing this for me. This is really for geeks. What I had her do is say, what is the big deal about this cord being continuous to that cord? What if we put a hinge here and didn't carry it continuously across? It's kind of interesting. What happens is your bending concerns aren't, because we didn't quite flatten it out the roof pitch. The bending concerns are now only down in here. And you'll notice also what happened, which I looked at, and because I'm such a timber geek, I can just stare at this sort of stuff. You'll notice I've got 5 kips of compression in this strut when I do this, but when the cords are continuous, I've got, where is it? It's there, 7 kips of compression in that strut. So why? What? I put a hinge in here, I cut this into 2 separate members, and my load goes down here? Well, actually, yes, because this is a continuous span across here. So part of what this compression strut is doing is not just taking the deflection out, but inducing flat curvature in there. You're also pushing it, you're pushing this straight in here. So because another way to say it is a continuous span has a 5/8 reaction instead of a 1/2 reaction in the middle for you engineer geeks. But the fact that this is continuous across the support means there's more force in the support than in this instance, where it's 2 simple spans across there. The force in this goes down. You'll notice the tension here and the compression here, almost no change at all. All it really did is a little bit of change right in here. So that's enough of the geek stuff. Let's go to the next one. This is where we've got either panels or boards or something in here distributing the load. And look what happens here. In order to get this top cord to work with this load spread all the way along here, and that's both the dead load and the snow load up here, this top cord had to go to 8x16. You'll notice that the compression tension didn't really change. It's still about the same, 20 and 15. But this had to go up to an 8x16 to handle the extra bending. So it's really, what's really paying the price is your top cord if you're distributing these in these ways, is if you're using purlins and boards, and what was the other one we had? Purlins, boards. We're getting to the next one. Okay, and then how about if we do the principal purlin? This is a principal purlin. Well, there's an eave purlin, which is, look right away, the eave purlin is taking a lot more load off than when it was when the purlins were at 4 feet on center. It took 1 kip away. When we put the kips, when we put purlin here, put purlin here, put purlin here, you'll notice we got 3 kips that are completely off the table anyway. They're not getting to the truss at all, right? And then I put them and I locate them. I locate a ridge up here, the common rafter, or boards go up here, or panels go up here. This is a pretty ceiling. That's my favorite ceiling. and then I have this big load, but it's right here. Look what happens in here. My top chord, the king post can only be an 8x8. The top chord can go to an 8x10, and the bottom chord can be an 8x8. That's just, this is the most efficient way to load this truss. The next step out is really, if you're really, it's the same truss, but we're going to have a ridge beam on top of this thing. Ridge beam, so the rafters span from the ridge down to the eave. What happens there, a lot of load just goes right to the eave right off the bat. Look at this, it goes right to the eave right off the bat. And so by now, all of a sudden, instead of having 20 and 15, now I'm down to 11 and 9. Well, that joint just got an awful lot easier to load right there. You'll notice, and we could talk about, I'm not going to, but you'll notice you still have quite a bit of load in the king post has quite a bit of tension because these are still working pretty hard. Okay, so let's talk about, I don't count on these, but they are handy for holding things up while the real lateral load components are being installed. So what about these knee braces that jam in here? Well, if you put a realistic side sway on this thing, if you really are building a dance hall out in here, you've got a church or something like that, and you're putting the braces in here, this thing, if you say I've got a tension brace that can, I've got some sort of knee brace that can handle 4 kips of tension. That's a lot. That's 2 big pegs and end distance to help develop it. Then it's still going to sway an inch sideways, probably more than anybody wants it to do in a wind mode. If, on the other hand, you're more realistic and say, you know, this thing fails, look at it, I don't bend that post anymore, but I doubly bend this post, it's in trouble, a lot of trouble, and my side sway goes up 1.8. So I'm not saying don't put these braces in. I'm just saying that you're working the post hard and you're also cranking on a bottom chord, which might not be big enough to really do a stiff job of it. So you can be breaking bottom chords with these braces too, if you really think they're carrying the load stiffly enough. So what about scissors? How bad does this get? I tell people, you know, the minimum force in the bottom chord is going from here to here. If you raise these if you break it into 2 separate bottom chords and raise them up all the way so they're parallel to the upper chords, the tension goes to infinity. So if you're halfway there, if you're from 0 to 4.5 to 9, you're halfway to infinity. Well, infinity over 2 is still infinity, right? So obviously I'm lying to you, but you are not being efficient. Look what happens when we use these same spans, the same spaces, same loads. Watch what happens. It used to, remember this, it used to be 20 in the top chord and 15 in the bottom chord. And before I leave this, let me say this about this king post. We'll see why, but this, if you have to leave this out for whatever misbegotten reason, brace yourself for trouble. This king post is seriously in tension. It's what makes this a truss, 1, 2, 3, 4 triangles, and not some frame which bends these poor bottom chords and bends the top chords. Oh my, I have done it. I am here to tell you, that is, if you have only one thing you take away from this talk, do not allow yourself to get talked into just leaving that member out because somebody thinks it looks cool. I want to run a big duck down the middle or something. So here you are. What happened to that bottom chord? The top chord was in 20, now it's in 34. The bottom chord is in 15. It's almost doubled. We've almost doubled. We're not halfway to infinity, but look at that. And then the top chord and the king post that used to be like 8,000 pounds or 8 kips, it's tripled. Because now it's not only handling, notice there's compression, these weird sticks, and this is the crux joint. This is the tough joint. We'll talk about this joint. This is a tough joint scissors. I got one, if I do, even sometimes I'll leave these timbers out to make it just a 3-way joint. If you have these in here, you've got 5 members coming together in one spot, and they've all got a lot of force, and this one's in tension, this one's in compression, this one's in tension, this one's in compression. This poor timber changes from big tension to some pretty good size compression. Just on the other side of that, there's a lot going on in this joint. Take this joint very seriously, and that's one of the ones you got to pay attention to, is the king post tension. So that's enough about members, and that's enough about orientation. Let's start talking about the connection, because trusses, to some extent, if Dennis Markham's on the call, there he is. These are the 72-foot long single bottom chord pieces of the Proctor Academy in New Hampshire. They promised us we'd be raising this thing in summer. This is when the GC finally called us, but you've all been through that story. So let's talk about connection methods. So there's mortises and tenons. That's what most of us got in here. That's what I studied in graduate school, but they really have limited capacity, and whether they actually justify the damage they do in a well-engineered truss, a well-designed truss, is running pretty efficiently. And you start taking housings and tenons, mortises and pegs out of there, you're really doing a lot of damage. We're going to talk about notches. These are classic. Notches are timeless, but they are compression only members, and we'll talk about that. And they do weaken the timber at the notch, and craftsmanship is involved. You need nice bearing, and bearing changes is the problem with dealing with wet timbers that are going to dry in place because the angles change. So it's really relies on nice craftsmanship. Some of these, they'll have cast iron standards to sort of industrialize and standardize the notches. You'll see some of it, and we'll see some of these later. Rods, I call them prices because they're tension only. They're very, you can look at it and tell what it's doing, what it should be doing, and all it can be doing. You can't, it might not be fooling you. It's not going to be in compression. You can tell when, so I love rods for their clarity of vision. Screws has only been recent innovation. I so far mostly use them to reinforce and repair and hold stuff together while we're tipping it up. Straps, we'll talk about straps. Straps are almost like screws. You'll see an example where we detail the straps so they actually look more like a screw. They're only in tension when they're done right. The simpler your load paths, the better. These are a straightforward load path. More than tenons aren't, but a notch is very straightforward. Rods are pretty straightforward. Screws are remarkably straightforward. These straps are very straightforward. They only do one thing and they do it well, and they're not going to surprise you by carrying things like side plates, which are fraught with issues that can transfer all these unforeseen things. You need to, if you're analyzing do a computer model that uses big side plates, you really ought to be including the side plate in your model to analyze it, because it can be so big compared to the truss members, and it can carry so many different forces that one of the biggest problems I see is people throw them in there on top. They'll do a simple pinned analysis and then they'll throw a side plate on it. And bad news, bad news. So here they are. These are, let's just say these are my favorites. This is it. Parallel cord trusses, parallel top cord, parallel bottom cord. Their rods are in tension because they are keeping the rectangular, they're keeping the rectangular bays rectangular by acting in tension. They point down towards the middle. You'll notice they get smaller in the middle. That's a bigger rod than this because the load's getting bigger as you get closer to the ends. And interestingly enough, if it's a hung top cord, this bottom cord doesn't even really need to be there. You know, it's not, because the tension is taking all the force up to there. There really isn't any force in here, so we just ended it right here. In this instance, we also used rods that went down through handrails and held up a suspended donut-shaped balcony below this thing. It's kind of fun. This is a ridge truss in a building down on the Cape. This is one of my favorites. This is, I don't even really remember where I got this thing, but this is an Industrial Revolution classic. Compression diagonals, lightweight top cords, lightweight bottom cords, crucial vertical tension rod in the middle that handles the compression in these two struts. These are optional. These two rods are optional. I only put those in if there's likely to be a lot of load hung on these bottom cords where you don't want to act as a beam from here to here. This is fine for tension, but it does reinforce it if you start loading your bottom cord. And one of the sweetest things about this is you'll notice these double-stepped notches. This is so elegant, and we'll talk about this joint. You see how it looks when it goes together. Very elegant joint. So this is connection basics. This came out of a text. This is one of the texts. I keep it right there. I can grab this thing. This is one I used when I taught undergraduate and graduate level timber structures courses. It's Hoyle's Wood Technology and Dynamic Structures. It is so focused. It was the most design oriented of what I consider the American books. And it points out this crucial, simple thing that I see people miss this all the time. Here's a truss. Here's a truss. When it comes down, it sits on a wall. Top cord, bottom cord, same compression, same tension. People don't look at the joints. What's the difference here? In this one, the top cord sits on the wall. In this one, the bottom cord sits on the wall. Is that a big deal? Let's look at how the force is transferred between those two members. When it's located like this, when it locates like this member is simply sliding by this pin, and this is loaded parallel. The top cord is loaded parallel to the grain. All it feels is that. But on the other hand, the flip side of that P down here, when this connection here, which feels the support, the bottom member, it feels the support, but it also feels this angled load from this pin. This pin is parallel to the load transferred to the pin, parallel to this one, but it's at an angle to this one. On the other hand, when I support the top cord, and now the reaction is here, there's only simple tension here. This is just the simplest tie as it can be, is in this member, and that member now feels the load that's parallel to the grain, and this member feels the load that's at an angle to the grain. If you don't think that's the difference, you haven't been paying attention. You've been getting away with stuff. If you don't think there's a difference between whether this is loaded at this angle or this angle. Now, when you use lots of little connectors, it's not as big a difference. When you use lots of little screws, and if you're using a lot of little pegs where they don't really behave that differently when they're loaded per angle to the grain and parallel to the grain, okay, but you're not doing that much. You're using bigger pegs. This is a fascinating joint. This is a double step one, and it's double stepped into both. It's a sandwich. You're looking at a 6x16 rafters, and you're looking at 6x16, 18 that sticks out through the top, and that is split ringed. This is split ringed, and this one is split ringed into the two bottom chords, and then these two notches go across. These two notches go across all three of these members, the three in the top sandwich and the three in the bottom, and then they're bolted together, and there's a pin right down here at the concentric point where the thing is supported and the lines of action of these two chords meet. This is a fascinating joint. It really is. It combines this, and this. How load sharing happens between here, that's a good question. I would certainly want these to be split rings and not shear plates if I wanted this one to carry, and see that looks like it's a split ring or a shear plate. The problem with the shear plates is they let this centerpiece slide a little bit, so this isn't going to be uniform bearing across these two patches. But on the other hand, split rings are much stiffer. Load transfer is much more immediate, and you would have more even load sharing between the three sandwiches when they get these two notches. Now, what about these two notches? These are crucial notches. Each one has to be nicely parallel to the other one. Has to be a nice uniform bearing, not tight here, tight at a corner. But not only that, this one has to be that, but not only that too, they both have to be very carefully but they both have to, all four faces have to be carefully cut so that you get uniform and simultaneous bearing across all these faces. A good trick. Sometimes what I'll do is, I'll undercut one and drive a pair of wedges in there and drive them in hard. Now, the problem is that crushes, so the load sharing doesn't stay even. But if I have any concerns about the capacities of the timber framer to do it, I'll have them put wedges in one of these.
Ben, may I interrupt you here? We got a special request from Janet that you remove the green lines. It appears to be distracting.
Yeah, I know. I can't. I don't know. Okay. Maybe, yeah, they don't show up. They don't show up on any screen. So I don't know how they got there, but.
Okay.
Can I apologize to Janet privately later?
Well, we'd rather it were public, but yeah, okay.
Okay. All right. I'm sorry, Janet. I don't know where they came from. Sorry, babe. So let's talk about this. This is this is a plan. This is a scissors truss, and they just slapped this on the top chord and the bottom chord, and they said, well, 6 bolts is a fine. This has probably got more load in it than this one, so why is this and this? Who knows? The problem is we don't know what the load transfer is between them, because this is an eccentric load path, and I'll show you why this is an eccentric load path. So this piece of steel is being twisted out of here, and why they didn't just cut a simple little notch in here and be done with this thing and some screws, I just don't get. But we don't trust notches in engineering school, apparently. So there's a PE seal on this thing. I have used this thing, it jumped off because I have used this in talks to engineers, saying this is what we sort of wish. We wish that the bottom chord tension is transferred in pure parallel to the grain tension in those 2 bolts, and the top chord compression is loaded parallel to the grain in these 3 bolts. And because it's got more force, maybe I'll have 3 of those instead. But I'm hoping they're parallel to the grain. This is what we wish. This is not anywhere nearly what is happening. The problem is that if I just looked at that plate would be moving up and down. It would actually be moving down because these 2 tensions can't do anything about keeping this plate from moving direct, and these things have a component. So this is not what is happening to this plate. That's what we wish it is, and that's what it looks like people design these things for. Notice it could be if I brought the plate down here and grabbed it and had it bear right on the reaction, maybe you can do that. Maybe he could do that. If these plates actually bore on the support too, then it'd be a much more complicated, but in some ways much simpler steel strap. Then I would have I'd have compression, tension, and the support reaction. But they just put these on here all the time. And just because it's cut into a fancy elbow doesn't make it's the same thing as if we're just a big old triangular plate. So here you are. This is what's really happening is that let's say it's supported in a way that this is in pure tension. Well, these are fighting it exactly. They are at least in balance, so the thing isn't going sideways. But that is an eccentricity because the center of these 3 bolts misses the center of action of these 2 bolts, and that's the eccentricity between this compression shove, this net compression shoving this way. So this is simpler but more accurate, but this isn't anywhere nearly the case either. each one of these things is going to have a perpendicular component to keep this thing from rotating about either here or wherever you choose to rotate it. There's going to have to be perpendicular components, which are going to be basically, another way to look at this thing is, you push on this thing hard, you're going to be, if you push hard on this, you're going to pry this out of the end. Now, one of the ways you can do that is to move this pattern of bolts down here so this line of action passes through that center of line of action of that. Then all of a sudden you've gotten rid of that eccentricity, and we'll show you that, how to do that. But if you're stuck sticking these things all on the upper side of this line of action, you've got eccentricities. So here, this is what we did on this one. Here they are. These are pins. This is not, these are separate straps. That's a bolt that bolts this strap to this strap. These things are really held in by dados. So that's a dado bar that's set into a dado face, and 2 bolts that go through there and clamp, and a pin here. And you'll notice when this thing is centered, so there's a pin here, there's a dado bar here and a dado bar here. So this line of action of that tension, that scissors truss, passes through the centroid of the line of action of these 2 dado bars. So this is using straps. They look like a cover plate, but this is really a pair of straps designed in this similar in that this is an overlap set of strap. I think that's a Y and a vertical. This one's not so critical because this is pretty symmetrical innately. But this is a way to get rid of the prying in here and use straps. I kind of like the way it looks. This is not for everybody. So let's talk about this. I've seen some really goofy things in my life, but really this is right up in here. This is really right up in here. And notice this, when I've highlighted in red, preliminary drawings, not for construction. What does that mean? When you see that drawing, that means some poor timber framer was jammed into a corner on schedule and budget and took them out and built from these drawings. That's what that really means. So sure enough, they built from this drawing. Oh, am I doing things by, no, that's not it. I wondered if I was inadvertently making marks. So here we go. Whoa, I'm going the wrong direction. I was trying to make that green mark go away, Janet. So here you go. So what is this thing? It's a house. It's, I forget even how long it is, 46 feet by 64 feet. The architect decided the way to do this, the impressive, cool way to do this is span the long way with 64-foot scissors trusses. Oh my. So you look at this thing and say, well, this one's all in an end wall, so it's only got half as much load. This one's in an end wall. They've actually got an end wall that holds them up. So these are kind of pointless. There's really expensive wallpaper. This one's completely engulfed in closets, full of shoes, closets. So you can't even find this truss. It's so buried in closets. And this one is sitting on a wall that goes all the way from right underneath the truss, envelops the truss because the bedroom's over here. This one's sitting on a wall. So it's only these 2 Burr rascals out here in the middle, which is dominated really by a fireplace. Only these 2 trusses are working. So why they didn't just come in here and build 2 or 3, make it look like a Swiss sleigh with 46-foot long beams instead of 64-foot long trusses, I don't know, because they could have picked them up in the middle on this load-bearing wall. This would have been easy. This thing is a mess. Not only is it a mess, the architect approved these drawings without noticing there's a dormer here and a dormer here and a window here and a door here. So they came in afterwards, cut these out, and this was already kind of a tippy thing. I mean, this is a pointless timber. It's got almost no load on it. What is this big, tall, heavy timber doing on top of those posts to have these trusses other than making it a tottery, dangerous looking situation? Then come out and cut them off in the middle and take out the braces? Oh my word, this makes me hurt even to look at it. But the thing was, so here's what this joint looked like. 66 kips. I mean, this is a lot of force. 66, you know, we've built houses don't weigh 66,000 pounds. All right, so we've got houses out there shoving through on this steel plate, and it's full of pins. These are all 3/4 inch pins going through a single plate. I think it's only a 3/8 inch plate too. This is eccentricity. The load that, most of the normal force here is in bearing along this face, but there's a big amount of 60 kips of shear going along here. And notice the line of action here is 10 inches away from the line of action here. So this plate is being spun counterclockwise too. This isn't a whole lot better, but that's a lot of force. This thing creaked and groaned and snapped and cracked, and it was 8 years old already, so it wasn't drying anymore. Things were moving. So what do? There wasn't, we tried to come in here with screws. You couldn't get to them. You couldn't come up with long screws buried in walls. Couldn't come through the top. It was a beautiful clay tile roof. So it had to be face-mounted stuff. We tried all sorts of discrete ways to do it. It had to be face-mounted stuff. These face-mounted straps look like individual screws. That looks like a big, long screw in tension that's keeping this thing from sliding and sliding. So that's the plan. They're on inside and outside, both ends of the, I think, 3 or 4 of those trusses. Before we did this, because this is early in the early days of these new European high-tech screws, so we thought, well, let's just go see them. Besides, the client could afford this, and we really want to know what we were doing. So we built up some models. We ran them at different loads to the grains, simulating these screws, and put them into the same steel plates. We did this for a couple of things. We wanted a proof of concept. We want to see, well, you know, these things are worth, you know, like 2,000 pounds of screw. Come on, you know. So, you know, we wanted to see that we believed that. We wanted to see what a failure mode looks like. Mostly, I wanted to be able to tell the builder and anybody else, whoever comes and looks at this thing, if you start seeing these heads rotating in this way, then you've got a problem. You know, we wanted to leave a track record of what the failure modes look like. The builder who was going to install them came down and learned a lot about what kind of impact tools needed, whether you needed a pre-drill, what to expect, how long it's going to take, how heavy these plates are going to be, what these screws are going to feel like, and things like that. Then, of course, the engineers got a lot of fun, and we made some money on this job. So there it is. This is undoing. Unfortunately, you can see the pins. They plugged the pins. They were small patterns pins. It was, you know, not a bad idea of a bunch of small connectors. It was just way too few of them with way too much eccentricity. So what about if you just did rods in this crux and we don't have, notice these top chords are big enough, we don't need the upper part. You can just make it, this is as simple as scissors trusses get, and this is a tension rod. Notice this in less tension, so it's smaller diameter, and then this is about as simple, and you can adjust it. It's just a heavy hoop to handle the tension and the modest tension. This thing's pretty, and it just goes right on out through here, and I forget if this goes right through the post. I'll talk about that in a minute. But this is subject to, you know, there's a lot of wind. This is on some mountainside in Vermont. I could tell stories about this for half an hour. But I wasn't too worried about stress reversals because they were going to keep building this house and land another piece of the house on top of this beam. So I had a house going to get built on top of this truss over the pool. So I wasn't too worried about wind load putting these in, trying to put these things into compression. But that is all. If wind came in and lifted this thing up, these things would rattle and clatter, and it would be nasty. So let's think the stuff, I mean, this is the crux joint, you know, here it is. I mean, everybody wants these things flush, which means, okay, that means a half dado here and a half dado there, which means eccentric load paths around the dado, or it means you've removed at least half of the capacity. It means all sorts of compromising to these two timbers. But then I've got this serious tension. How do I get this tension into this? How do I get this tension around these dado? I have drilled a slot down between the two dado faces, then this needs to get better. Notice this was using up a bunch of leftover recycled planks that South Mountain had out on. So for a while, for a couple of years, I was coming up with stuff that used up, like this wall, coming up with ways to use their overly optimistic purchase of a lot of recycled Douglas fir planks, heavy planks. Here we are. So this is what I call a clasping king. So it's in, we got simple Burr's melts up here, but then this clasp goes around, it's split, and you'll see this in a second, it's split so that this is actually compression, nice cushion compression bearing on the underside of this. We're not damaging these dados any more than they already were. So there they are, and there's the split king post. You'll see there's a dado in here where that's a half of a plank wide. The other one is a half of a plank wide. And so that's a simple Burr's mount. So that's a Burr's mount down in here. You'll see this joint in a minute. And then all the compression is on these two surfaces. So let me shut off my cell phone or throw it in the toilet. So here are the two together. After a while, I get bored with all this, you know, prismatic stuff. So I talked them into spinning the king post 45 degrees just because we could. And so there it is. And so they're clasped, and now they're going to trim this off. And we had a contest for what kind of detailing are we going to use on the bottom of the king post here. But this is a crucial amount of this gets hung below to handle the compression on the other side to deal with the tension, and then a Burr's mouth up here. So let's talk about these, which I consider these scissors trusses, really. They're just a different kind of scissors truss. They're smooth, they're bottom chord, curved bottom chords. Used to be I didn't have to worry about these things, but then architects found themselves with CAD drawings. So all of a sudden it got to be pretty easy to draw a 28-foot diameter radius circle. Used to be you had a holometer, you had a template, and to draw a 28-footer, it wouldn't fit in your drawers, you know, so nobody did it. You know, you never saw this in the old days, but now CAD, I can just do any circle I want. And I started seeing these things, and there's some things about this. This is a scissors truss. The good news is that because this thing is radiused up, you generate more interconnection along here. Instead of when this is a straight member, that shear plane, the interacting shear plane, where you want to try to make your connections, you do have more of it to work with. That's good news. The bad news is this is a curved member. Curved members, when I pull on them, and this is still in tension, when I pull on them, two things happen. One, I straighten it out, which means already I got some deflection in here. We're not even going to talk about truss deflection, but that's a huge topic because, you know, most programs include no connection deflection at all. There's no allowance. They assume them to be perfectly pinned or perfectly rigid, but we all know there's slop in our connections. The timbers shrink, this shrinks. We all know there's slop in our connections. So any computer analysis you get of the deflections is going to underestimate, I'm convinced, the amount of deflection you're going to see because of changes in deflections within the joints, which is very difficult to model. Anyway, so the good news is you have this. The bad news is that now I've got tension in this member, which is straightening this thing out. So the thing's going to, because of that straightening, I'm pulling this thing straighter between here and here and between here and here. The thing is going to spread more than a scissors truss would. A scissors truss would not, it doesn't have to deal with straightening members, elongating members. And also the thing that happens is when you do this, you're inducing bending in here, you're inducing bending in this member as it gets grabbed in the middle because you're trying to really pull it from here to here. So you really lifted it with this king post. It really wants to be down here. So I've induced bending by pulling it up. And I've also induced tension perpendicular to the grain by straightening out a circle. Like when you start to bend a curved member, you are inducing, try it yourself with a deck of cards, bend them, and then try and straighten them out. You separate the cards, you separate the timbers, you're inducing tension perpendicular to the grain, which is timbers, Achilles heel is chronic weak link. And that's what, so if you're doing this with Douglas fir, which is notoriously weak in tension perpendicular to the grain, if you're using these, you may find yourself, as I've had to do, reinforcing them with screws from above, radial screws that keep it from splitting as you induce that tension perpendicular to the grain. So then what do you want to do? You want to do as minimum damage to this one piece bottom chord as possible. So the tension here, I could have taken a rod through here, or we could do, oh, here it is, how to grab a curve. By the way, if you don't recognize him, that's what's his name? Norm Abram, thank you. And this is his own house. And that's Ted Benson. Don't do this at home, disconnecting the cord. Later, in the act of taking the shrubbery down off that same ladder, trying to emulate Ted, he slips, the ladder falls out from underneath him, he falls off the ladder, hits the staging, rolls off the staging, and hits the floor. Another story. So here you go. So how do you do the minimum damage to this curve? By not even taking a cord, not even anything more than a locator nub tenon. So you take this beautiful piece of wrought iron that looks sort of like a crown on the king post. Anyway, it goes down past the curved bottom chord and turns what is a tension connection into a compression member by now these two wedges bear on the other side. So these things are sized so that you don't crush the wedges and you don't crush it. So they're wide enough you're not crushing. And you're also, they're deep enough so that they can handle the bending because this is uniform load in here and 2 point supports over here. So these wedges are pretty exotically loaded in crushing and shear and some bending. So here you go. But it is a way to get away with this curved bottom chord. There it is in situ, kind of pretty. And then what about this at the end? You know, there are these elongated shear planes where we can transfer the big tension to the big compression. And the shear keys are about as good as split rings and shear plates. They keep the load instead of a big curved cover plate or a big old strap. You keep the eccentricities. It's just taking tension here to compression right there, tension right here to compression right there. So minimum amount of eccentricity, innate eccentricities in your load flow of your connection mechanisms. So I've been bad mouthing them, but you can do it. And this is one where it's another sandwich plank. We had some brand new sandwich planks. The owner wanted this plank look. So these are goofy, not used at all. This is too steep. But really what I'm here for is showing you this. This is a big fancy piece of glued up plywood that's in the sandwich. And then lots of pegs. And then it's supported in a way here. So this is on the support, not this is on the support. This is whittled away on the underside. So this is a pure tension. You don't have as many of them as you do in here because this is in compression. Although this is not symmetric, it isn't too bad. You know, the line of the eccentricity, that's the line, the center of this bolt, the peg, and this is all pegs through the sandwich. So if you're going to do it, you can do it with some grace in here. Wood is more compliant than steel in many ways, both in temperature and in moisture. And you can drive interference fit pegs, so the pegs are tighter than bolts. It's sandwiched, so it's hidden, and the tolerances are relieved. So I don't have to worry about whether the pre-drilled hole in the timber is going to hit the pre-drilled hole in the steel. We drill them all at the same point. Clamp the whole thing together, drill a bunch of holes, and drive a bunch of pegs. Feels pretty familiar to everybody on this call. So let's talk about notches. And notches have been studied for a long time. This is an old Russian text. This is another book that's right there. I mean, I can touch this book from where I'm standing. This is a recent English text. It's a little more remote. But this is how long people have been studying this thing. Notice this. The Russian text goes into examining what about the nature of the bearing stresses as a function of whether I have a gap here, so it's just pure bearing, or if it's tight in here, all of a sudden I can have bearing between these two surfaces. What's that do to the angle of attack of this? And what if I actually undercut this thing like that, and as I push down in here, I can pry and induce splitting. This can lift up off of that point. All these things change with the change in angles as they dry out too. This is all interesting. Then there's this simple bearing, which we'll talk about this. This is as simple as bearing faces with a sandwich in between. And it's perpendicular to the angle of the compression. On the other hand, look at this English text and see they've got that same gap. You know, this is written in the 30s. This is written in the 70s. You'll notice here that angle in here. This compression member is coming. There's a tension rod and a compression member diagonal. You notice that isn't perpendicular. So there is a tendency for this to slide, and we're going to talk about that tendency to slide. So there's a lot of compression here, but they also put this equal angle bearing face in here, and then you'll notice this is in there with shear plates or split rings or something to counter the tendency of this thing to slide down there because it's not coming in at perpendicular angle. It wants to slide, so it's restrained by bearing here with the and we're going to talk about that here in a minute. This isn't the end of it. Industrial Revolution was really the heyday of heavy timber trusses. They would build load-bearing masonry walls and then put heavy timber trusses. They had catalogs full of hardware, cast iron hardware, wrought iron straps, all sorts of fabulous stuff. They were using shear keys. They were using straps. They're using shear keys. They're using washers. They're using castings, wrought iron castings like this to transfer. Look at this. They're dealing with 25,000 kips, 25 kips, 29 kips. A lot of big loads in here, and they just came out of catalogs. This was nothing. This would be a 150-foot span truss, and they did them all day long. They knew what they were doing. This was, see, they have a double bearing notch in here. They had a cast iron shoe that was dug in here to keep it from sliding. Corbels in here to reinforce for the notching and the damage. They got corbels bolted in here. Here they have we'll see it in a second, a temporary alignment block. Was that, see that temporary alignment block in there to when you locate the load, that truss on there, you can tell you got a light. I mean, these people, this is really sophisticated stuff. This is right out of the current German code. You'll see the equal bearing angle in here. They'll split this. This won't be at 90 degrees to this. It won't be to 90 degrees to this. They will pick this angle. That's the germane part. But this is right out of the code. You can use this in Europe right now, and these are full of some, what are the capacities of the joints as a function of the angles and the end distances. So let's talk about this. This is all new. It's been bothering me long enough. Finally, I said, okay, here I am. Let's figure this out. Let's talk about bearing versus friction in joints. I can't tell you how many times I've got trusses, king post trusses, 12-12 pitch, and we'll use a simple bird's mouth down at the bottom. Then all of a sudden I'll get up to the top, and it's the same force. It's the same angle of attack. And all of a sudden everybody wants to use this sloped shoulder. I say, why? I mean, this works so well down. It works so well down here. It's not hard to pull together. You can slide them sideways. If worse comes to worse, you can put them in and then drive the king post down and get this to fit. Just because you're going to pivot this in, this relies on friction. Ultimately, at some point, this relies on friction. Let's talk about friction. This is a slope shoulder used as a bearing joint. Now, I see it more recently than I do in old timber trusses. The Industrial Revolution didn't do it. The English don't do it. The English don't do it. The Russians never did it. It's really us who are doing this stuff. So here we are. So what happens? So let's talk about the coefficient of friction. This is really kind of fascinating topic for Brungravers because my father is still alive. He's a PhD structural engineer. And he took a sabbatical one time, worked 2 years or 3 or something for the Bureau of Standards and developed a slipperiness tester. The National Bureau of Standards Brungraber Mark II slipperiness tester. And this is really it. He took a bearing pad and tipped a weight over and measured the angle at which the thing slipped. So what we're talking about here is at some point, if this thing were flat enough, you know better, you're not going to count on it for slipping. The question is, where is that point between perpendicular and where everybody knows it's going to slip? Everybody knows it's just going to slide. Where is that point? Well, it turns out that's been a issue of interest for a long time. We have this thing called the coefficient of friction. And what it is a simple ratio. I wish it were pinned down, but for wood-to-wood connections, the coefficient of friction goes anywhere from 1/4 to 1/2, which means basically that the friction force you can generate at out of any one of these surfaces, that friction force as a ratio of the normal compression force that's in there, and see the C, there's the compression that matches this. You can divide it up into a normal component and a friction component perpendicular to each other. That friction force is somewhere bigger than the least it's likely to get is a fourth of this, but the most it's going to get is half of that. All right, so it's going to be less than or equal to half of this, so it's going to be more than equal to a fourth. Well, what can you do with that information? Well, a lot of stuff, but what I chose to do with it is said, I'm going to use a factor of safety of 2. I'm going to say that no matter what, I'm going to say I'm not going to count on friction for more than half of the minimum that I can count on. Let's say a factor of safety of 2. I'm going to say that my friction force is never going to get bigger than my normal force divided by 8. If you look at that angle, what's that angle? There's that angle, theta. What's that angle? It's the angle arctan of 8. For those of you who always wonder what that arctan or that tangent with a -1 exponent was, that's the arctan. 83 degrees. In other words, I've got to stay within 7 degrees of perpendicular if I want that to reliably stay and not slip. Where is that in? So I spent some time, I'm embarrassed by how long it took my trig or my geometry or whatever it was to get caught up with this. And, you know, talking about this angle theta between the compression force you're trying to transmit. I'm neglecting this face like the Russians include. What is the compression? What is that theta? Well, it turns out it's alpha, the angle of the timber, the two timbers make with each other, plus beta, the angle that this notch makes with this notched timber. I'm sure this is some function of that too, like whatever. You'll figure it out. Anyway, alpha plus beta has got to be bigger than 83 degrees. And so I'm convinced this is true. And so you go back and look at your slope tenons and you add this number to this number, if you're above 83, or you can go, feel free to go mess with your factor of safety, help yourself. But check these things out and see if you are indeed counting on friction to an unreliable extent. So let's talk about some stuff that I see more and more. I don't see this in the Industrial Revolution. I don't see this in the 100-year-old Russian stuff. I see this in modern timber framing. I understand why people do this. They say, well, it's triangles. It looks like truss. As a matter of fact, I've done this. All right. So I've even done this. So I mean, and I've certainly put my stamp on a lot of it, but I got to tell you that I'm concerned and we pay a lot of attention to this joint. So what's happening here? I don't even understand how people raise these things. You have to pre-assemble this thing. And so this is a really delicate joint when you got to pick this thing up really carefully so that you've got almost all the load as soon as you pick it up. So one person could hold these two posts up, or one person on each post, to carefully lower them down so you don't wrench this poor joint into multiple pieces. What you're doing in here, instead of bringing this top chord up to where it really wants to be, you're putting an awful lot of shear and bending depending on how far up that is. Now, if you don't think, and I bet everybody in this room has seen these things, if you think that's not a problem, look at this. So this is about 36 feet. I don't know who's actually involved, but it is a hotel building down. It is a hotel in the south. And there it is. Look, there's a sort of a scissors truss, sort of cathedral-y looking thing with sort of corbelled sort of braces. And there's a big gap between the top chord and the bottom chord cranking on these posts. Well, when I get pictures of this thing, this is what I'm looking at. That I've seen worse checks, but I can't tell you where and when. That is not good. That's more than screwing that together. That's bolting through bolts together. This is serious problem, people. This is really, and that's what happens when you push hard here and pull hard here and push hard there. You're going to get this sort of stuff sooner or later. So the question is, where are you in the continuum? You know, if you're up here, maybe you're getting away with it. If you're doing a good job of grabbing that post with this bottom chord, maybe you're getting away with it. If you go here, clearly you got a problem. So you got to ask yourself, do you feel lucky? So here you are. So look at this one. This had a PE stamp on it. Look how how many people think there's 2 L's in pavilions? I bet 30% of you, because that's about how many times I see it. But look at this. This had a PE seal on it. And you look at this thing and say, whoa, you look at this joint. I mean, not only are they, this would have been so easy if you just raised this up and put a notch here that hit it here. This would have been a fine joint and then landed on here. But now, you got to raise this thing, assemble it in error, assemble this and pick it up without wrecking this. When you can't do much at all without splitting that top chord and splitting that post and splitting this into a splintering mess, you've got a problem. I look at this timber, and I used to have a rule of thumb. I said, at first I said, if you can't drop a timber off a waist-high bunk without busting the tenon off, you got too much tenon or too thin a tenon or something. My other rule of thumb is if you can't pick this timber up by the connection, I'll let you have both pegs in here. If you can't pick this timber up by that two pegs that are in there, you do not have a connection. You have something that feels like a connection, but if you can't even handle the dead load of the member, if your joinery, your connections can't even handle the dead load of the member you're connecting it to, you're kidding yourself if you're calling that a structural connection. It may be good enough to hold it there long enough for the check to clear or something. This is awful. This is really awful. I saved it. It's so awful. So here we go. Sometimes you look up, and I just grabbed this off the web and I sent it off to my partners in total amusement. I love this thing. I just love this thing. I mean, I'm here to tell you, these are probably clear spanning log prones. There is not a lot of compression that's going down from here through this crooked strut. Now, maybe these top chords, maybe these boards are in tension, and maybe these 10 boards in this zone are actually making it so that then maybe there's something in here that maybe that light fixture can handle some tension. So this is in tension handling the strut in here. I don't know. I don't know. This is just on the web. But when it's on the web and somebody sees it, the next thing you know, they come to you and they want it. I'm telling you, what you got is you got a log tie beam, and maybe you got a log bearing wall, but this only goes up to hold up this purl, and these two are on their own all the way past that wall, all the way to this end wall. I don't know. I'm glad this isn't a heavier light fixture or a big ass fan. Anyway, you see this all the time. People see this and they say, oh, I want that. So at Brad Morrison, I hope he made the call. Brad Morrison asked me to do this. So I said, I can't talk about trusses without talking about these things. Dick Schmidt and I had the great honor and pleasure of going to see these things. This is way more truss action going on in these timbers than there is in the typical Hammerbeam frame, which is a frame, not a truss. I'm convinced. There's so many members in bending. All of these members in the scale of this building, they are mostly axial members. These are arched trusses. This is hangar number 2. There's an identical one right next to it, hangar number 3 at Moffett Field in San Jose. Hangar number 1, for those who are interested, is steel and was built. This is during the blimp age. The first one was steel and built during the dirigible age. And you know where the word blimp came from? Quick aside here. There's 2 kinds of LTAs, lighter than aircraft. Type A, which is rigid, dirigibles, and Type B, which are limp. Type B, limp. And there comes the word blimp. So along comes World War II. We're worried about submarines, and we're worried on all 3 coasts. We're worried on the West Coast, the East Coast, and the Gulf Coast. And you can't send planes up and have them hover there watching for submarines. So it was a perfect application for blimps, but it turns out, because blimps can stay up for 3 or 4 days, but it turns out that their operating range is about 500 miles. So every 1,000 miles along both coasts, all 3 coasts, Gulf, West, and East Coast, we built a pair of these hangars to maintain and protect them during storms. We basically built 3 entire coasts of wooden fortresses in less than 2 years. Each one of these things is 300 feet wide, it's 180 feet tall, and that's 1,090 feet long. There's 2.8 million board feet in what you're looking at, and the doors at both ends, I wish I could tell you about them, but they do not load this arch. This arch is independent of the doors, and the doors are 120 feet high and 220 feet wide. These things were designed and built in the first 18 months, if you can believe this thing. When they were getting good, the erection would take less than a month for each one of these things. So what were you in there for? Wow, yeah, they're having a lift in a rental rag top and a lift, and we're probably 160 feet in the air, and there's a professional operator, thank goodness professional, because he would get it up here and then roll forward. So you could feel, I mean, every crack in that concrete slab. You could feel as you bounce over. And when you're up here looking down at the chassis for this rolling this platform, it looks really small and completely on. How heavy can this be? Is there a huge magnet in this thing? And this is a steel slab. It just doesn't compute, but it worked, and I'm glad I got to do it. This is one of the reasons we're here. Minor dips. There's a minor dip in a ridge, but that ridge is 1,100 feet long, so it's not minor when it's 1,100 feet long. They were worried, rightfully worried. Look at these. These are the box beams. This is how they isolate it. The doors slide through this slot, roll on tracks at the bottom. They're precast, or not precast, slip-formed concrete 4 piers at each end that hold up. This is a box beam timber lattice truss with timber lattice are 220 feet long. It's a box lattice truss that is loaded. All it supports vertically is its own gravity load, maybe snow, but more than anything, it supports wind load on the top half of this truss. So it's loaded more horizontally. So it's a box truss, 220-foot span. In the context of this building, it looks like nothing. When you're in this, it's like 20 feet wide, 20-foot wide cube, 220 feet long, surrounded by 4 town lattice trusses. You are in another world, and you're 120 feet up in the air. Boy, am I excited about this building. Anyway, look at this dip. There it is. And so it was dip, and they needed to prop it up. So rather than just fill it with staging, which I sure wish they had done, they went out and they found somebody who could walk into a building that was falling down around their ears. They were starting to find big pieces of wood lying on the floor way down here. So they had the first safety meeting was in a 20-foot container with a whole crew, and they said, we figure it's going to take 14 seconds for this thing to collapse. So when you're up there and you start feeling it collapsing, you got 14 seconds, and our plan is to come down and race into this storage container, which we think will withstand the impact of all this landing on our head. You can see all the repairs that have been done to this poor thing over the years. Now they've propped it up, and I call this a wooden balloon and steel needles. These are 4-foot diameter pipes, 100+ feet long. It's like propping up a wooden balloon with steel needles, but pile drivers, that's what pile drivers do. They drive piles. They had a rolling scaffolding here. I'm standing on this rolling scaffolding. This thing used to have connections to that. That's how bad things are up there. They've been splicing glue lambs in here. This is not good. But look at the stuff they're adding up in here. All this is custom made, heavy stuff. And ultimately it's hanging on timber below. This is where I got started on this whole thing. I've got a ratio. I've done it. And that's another old talk, I suppose. But what about the weight of what you're adding compared to the capacity you're adding to? And some of these things, it's negative. You're doing more harm than good by hanging. You're adding maybe 2,000 pounds of capacity by hanging 6,000 pounds of weight up in there. This doesn't make any sense. On the other hand, put a bunch of reinforcing screws in there. You put 3 pounds of reinforcing screws to prevent the splitting in here. You run 3 pounds of reinforcing screws in here. Maybe you add 4,000 pounds, and maybe you add 10,000 pounds with 3 pounds to keep the splitting from happening. With 3 pounds of screws, you add 3,000 pounds of capacity. That's a huge ratio of value of load added to weight added. So I promised Mac I'd get him back. Here it is. There's Mac at Stanford. Help me do some of this is a shear test. And so I think you guys sit there and think it's hard on timber framers. Look what that does to the engineers too. That's Mac. What is that? 3 years ago? Okay, maybe let's say 35. And I offer this for all of us who are out there and you're looking to hire an engineer and you find yourself, you can tell I'm winding this thing down. If you find yourself looking for an engineer and you're worried about how scary they are down to how big a trouble they are to you, and you're looking for their boldness ratio, I'm convinced that we look something like this. As we come out of our various degrees, we're pretty confident we know what we're doing. Then we start to see things go unexpectedly awry, or the child's tuition bills start kicking in, or a mortgage payment, or a truck payment. And you start getting really conservative in these years, 35 to 45, 55. And I'm right in here now. So I'm well into the scary zone up in here, So I offer that to you if you find yourself wondering, well, have I got the right engineer for this job or not? And then here, I do this because this is a photo that's looking me right in the face, right below this screen. This is where I was on Woodstock weekend driving a Lotus Super 7 with a great friend. And so I just, anytime I have a chance to see the slide on a picture, that's what I do. So there I am. I thank you for letting me take a little bit of advantage of with you. And how am I doing? 10 minutes over. Holy smokes. I got yacky.
You're doing great.
Any questions, or is it people snoring? How are we doing?
We did not get a lot of questions on the chats.
Sometimes we might have lost everybody in an hour. Some of these calls, they get called on an hour. Is anybody still there?
Yeah, there we can see their face.
Yes. Okay. Is everybody just sitting there? Boy, I see a lot of crossed eyes saying, "Oh my God," glazed over eyes. Saying, "Oh my God, that was a lot of information." Hey, Jennifer, how are you doing? And everybody who recognized anything in there, I apologize if it hurt anybody's feelings, but I sure appreciate everybody having shared stuff with me over the years. And I'm happy to take any questions. Mac, I thought I was going to make these slides available if people want to do that. And frankly, I just assume have everybody write to you. Anybody who wants it writes to you, gives you and they can write it on a $10 bill too. But they can write and give you an email address. Then you compile all the email addresses. You send me that list of email addresses. Then I would plug that onto what I call a share file connection. And you could return email. Boy, this is the first I've hit. You can return email, and that would give them access to this, what is a rather big file. It's too hard to just send it. I'm not printing it out. So But I would
Okay.
invite you, if you're interested, send your email address to Mac and he'll compile them all. Okay.
Yeah, we'd love to do that, Ben. So, all right. Anybody that has a question, feel free to speak up.
Well, I guess I'm flattered. I answered every single question.
Hey, Mac, it's David Ornican. I have a question for Ben.
Please go for it, David.
Hey, Ben, go back to that smooth scissor truss and talk about the guys that try to build that curved member out of solid timber. What's that all about?
We talking about this one?
Yeah, the one with had the glue lamb curved bottom. There you go.
Boy, you know, I've got slideshows where I've given where people saw these things. You know,
Yeah.
You saw those, and what happens is, you know, it completely denies the fact that wood, typically speaking, is a straight grain material, which means that, particularly down in here and up in here, I don't have much grain holding that. That's just a little triangle of floating wood, and this is frankly just a long triangle of floating wood. So really, I'd be happy if this piece of wood, if I cut this out of a curve, I'd be happy if this piece of wood didn't fall off, let alone carry an awful lot of tension. So when people start sawing these curves, I say, well, show me what you're sawing it out of to assess, are we at least keeping, I want to see at least some wood that goes continuously from here to there. You know, you're losing it on the top of the outside and you're losing it on the inside of the inside. So I want to see at least some wood. And a lot of times I'll have to put a rod in there. There simply isn't enough. And if they don't want to go glue lamb curve, and I don't blame them, then they want to do that. But I've got all sorts of pictures where I've got splits right through here, just splits right along the grain, because that's what wood does, you know, and there's splits right through the joints, and then you have to, you know, reinforce it all and put it all back together. Does that answer your question, David?
Yeah, I thought it would be helpful just to point that out, because I get a lot of requests for doing that, and I have to go through the same drill that you do and talk about glue laminate or tension rods, because when you have grain run out, you have eccentric loading, and then you have splitting, and then the thing falls apart.
I've got a college buddy building a place out in the vineyard. I literally met the man 50 years ago this fall. And, you know, he's building something. He's got just a little porch with a curved top cord on it, or curved bottom cord on it. And an architect who I actually know and have worked with really well. But the architect wants to do it with just one curved plank. And he doesn't want to get it any fatter than an inch shaft. So he wants to do it with two curves cut out, two by 12s. And the porch roof is nothing. And here I am just saying, Alvy, I can't do it, you know? It's breaking my heart, but I can't put my stamp on something that I have so little faith in as this. So we're going to flatten the curve out a little bit, put a 2x8 back in here, and then you're just going to cut a big old piece of AZAC and cover the whole thing. So there's a way out of it, but, you know, I just see this all the time. And, you know, when I have to fix stuff, when I've found myself fixing things that went wrong, I'm really careful not to have that happen again on my watch if I can avoid it. So I've had to fix things that have gone wrong down there at that bottom. So unless it's largely ornamental or very lightly loaded, or we've come up with a way of making all the joints happen in the zone where there actually is some reliable straight grain that goes up into here. But these connectors down here, aren't worth much. They are not into anything like what you would call solid wood. You want them to be, and I don't blame you, but they aren't.
And we do have a question from Morgan. I'm not sure I understand it, but perhaps Morgan can jump in and explain if you don't understand it. So I'll just read it. For your slope shoulder connection, could you use some of the internal shear of the top cord so that you don't need to rely on friction only?
Yeah, I mean, you know, here's what happened. Where did I do that? I got to look over here. Where did I do that? Was that up here? No, it was way down here.
So.
It was late.
I think it was later. Yeah, friction.
Yeah, late. Oh yeah, here you go. All right. Yeah, I mean, I've all right. So I've seen ones. I think Morgan's saying, what about a tenon in here? And sure, that's actually, when I let people do this, I have a tenon in here. Now here's the problem with that tenon, is that you can't see. Usually it's back cut, so I can't see if I've got good bearing. So I really have to have faith. And if it's bearing, then this is maybe not bearing. You're trying to share a load between this stick and this slope. And the odds are good that it's probably on this stiff, but not if you didn't cut it right. It's really, now I've got two potential load paths, and I'm not sure which one it is, but I can imagine one where I undercut the tenon, so I got nice sliding, I got a nice tight fit here, I undercut and I left a 1/4 inch gap in there. All of a sudden, whatever reason, maybe a little lighter load and this thing bounced out because the load reversed, it slips, bang, and slams into, all of a sudden that tenon, this thing starts to slip out, bang, slips in and hits that block of wood up in here, that secondary load case, and that's a sudden jar. And now shear is, shear forces can impart brittle and sudden and complete failure. So I'm not wild about it. It's not, it's very difficult to cut this joint, period, let alone cut this so that you got uniform load sharing, because this angle gets tighter and this angle gets shallower. This thing wants to open up gaps left and right as these two members change shape. It's a little tough to predict. It's tough enough to get a nice uniformly bearing, consistently bearing. But then if you have this buried fitting in here, who knows how the loads share between those two? You can tell me all you want about, well, I got good tight bearing. So why'd you do it in the first place then? Because then the only way to do that was you had to pull this thing down. You had to pull this down. If you pull this down to get that to bear fit, then sure, why not?
And
Does that answer your question, Morgan?
He follows up. Sorry, that wasn't really clear. I guess I'm saying is that some of your gravity loads can be used coming out of your top chord to keep your joint in place. No. There's a question, no?
Some of my gravity load, I wish I could give them the pointer. Is this a better one? Some of my gravity load is coming. Well, I'm sorry, Morgan. I'm not. Morgan, do me a favor and write to me separately, will you? Or even call me. I'm not that hard to find.
Hey guys, can you hear me okay right now?
Yes, Morgan. Go ahead.
Okay, here we go. Sorry, my mic wasn't working there. Yeah, I guess what I was getting at is that you've got sort of internal shear coming out of your top chord into that connection. Sort of your gravity loads are pushing that top chord.
Yeah, there's a shear. There is a shear plane here. You are, if you actually succeed in biting into that surface, you are trying to shear that block of wood off along that plane. Is that what you mean?
No, I guess I'm not explaining myself very well. I guess, there's part of the loads that are implied to the building that are keeping that slope shoulder in place, are they not? The vertical loads that are being applied to that top chord?
Well, this is a little vague. I mean, for all we know, there's a huge ridge beam in here, and what's really happening, there's no load, there's no bending load applied to this at all. It's all ridge beam, and this is being shoved down through these two sticks.
Oh, sure. Okay.
You need context to understand really the load, the loads that are in here.
Ben, this is David. It's always made me feel a little bit more comfortable when I do this if there's a binder bolt horizontally across the joint to hold everything together.
Yeah, I like that too, to squeeze things together. And it says single shear, and people usually make it a sloppy fit so they can actually get the thing through there. It's really handy during raising, so you can put straps in here and pick the thing up and not pull the thing apart. So I'm into the binder bolt. I'm with you. You'll notice here, by the way, I meant to mention this, see that gap in there? The Europeans are very clear about this gap. And that means that when this timber shrinks and this point goes that direction, what you're not going to do is pry this and open up a split along here. I meant to mention this as I went by there. That's a deliberate gap, but it's not just sloppy drawing. That's a deliberate gap. And the Europeans are very adamant that be in there. Now, I've had almost this much luck convincing timber framers, oh, could you put a deliberate 1/4 inch gap in here so that when this squeezes down here, I don't actually touch and split this thing along here? You try and talk a timber framer into a deliberate gap along what they want to be a bearing face. Doesn't go very well. I see Robert Chambers.
Same thing on the bottom same thing with a upper chord to lower chord bird's mouth at the bottom.
Yeah.
Right, Ben?
Yeah, it's the same. This is
with that deliberate gap.
I could take this slide and turn it 90 degrees. It's the same joint. That's what I'm always surprised when I see, why would you use this joint down here and then use a completely different joint up here, which is almost precisely the same situation, generally speaking. But people do it all the time. I can't tell you how many times I'll see this down at the bottom and I'll see that up at the top.
There was one other question, Ben, that I thought you've touched upon it, and the effect of moisture content on the design of the truss, and knowing that you're working with green wood.
And I went through a pouty period where I said no more wet timbers in exotic trusses, heavily loaded trusses, because what happens what happens is, you know, just like this would shrink. It goes this way. It doesn't go that way. It goes, this timber gets smaller this direction, but doesn't change at all this direction. So that angle becomes more acute. So what happens is your angles, and that's one of the reasons the Europeans do this. That's one of the reasons the Europeans bisect that angle, is to cope with that. So at least they're changing the same amount. All right, you're not getting, it's the best you can do to deal with the fact that your bearing angles are changing as you do it. So, you know, wood is wonderful material. There are so many reasons I'm in this field, but one of them is the wood is so wonderful that it's compliant, that it allows us to get away with some stuff, so that when this angle gets tighter and the bearing pressure gets really tight, gets in, you know, the gap opens up at the top and it gets really tight. What happens is the two fibers, and particularly interstitially when you have the two bundles of straws, and so you don't have uniform bearing, what you have is a bunch of raw ends of straws bearing on the ends of a bunch of raw ends of straws. Those actually crush into each other more than if you take it. That's a more crushing surface. That joint, let me look at this. That joint right where you're getting end grain bearing on end grain bearing, you'll get more crushing deflection in here than you do in this one, because in this instance, you're bearing on the ends of the cell walls are crushing by you. And so it's on a micro level, you've got very intense stress concentrations. The edge of the cell bearing as it runs across the end of another cut edge of a cell. So these are compliant, and that's saved an awful lot of trusses. So when this angle changes and I start getting more bearing down here, well, it crushes in and distributes the load. Did that answer that question?
I think it does.
It is one of the reasons that, like, you'll see this angle and this angle, many times they'll split it.
Ben, you promised that you'd talk a little bit about compression, and it's kind of late to be starting back on a very broad topic, but you really didn't spend too much time talking about compression joinery.
Well, I don't know. I think I think a notch is a compression joint. And I think I beg to disagree. I humbly disagree. I'd say that to the extent I talked about notches, that's a compression joint. Mm-hmm. When you talking about the specific ones over here, like, I mean, that is, I mean, if you want to characterize connection methods right here, mortise and tenon does a lot of different stuff. Doesn't do it, frankly, terribly well in any direction, but it's a good compression joint. Notches that's all they are, compression only, right there. Rods, on the other hand, I didn't talk about them much, but I use them. The Industrial Revolutionists used them. Screws are pretty much tension, but you can use them because they're in tension. You can use them to generate shear across a connection. Straps are tension, and side plates are a mess. So to the extent that I tried to, balance notches with rod screws and straps, I don't know. What did I say in a casual way that made it sound like I treated the topic of compression lightly?
I'm sorry, I didn't mean to imply that you did.
You're forgiven. But let the record show, this was 4 years ago, before he became, this is what he looked like after 10 years at Fire Tower Engineered Timber.
I had less aspect than I have now.
You didn't have any ass at all. You were fun, though. Any other questions?
All right. Well, Ben, I'd like to thank you so much for regaling us tonight with what you've taken 40 years to develop. I really do appreciate it, and I'm sure everybody here does. And the only thing that I really have a hard time with Zoom on is that it doesn't allow us to clap at the end of one. But consider yourself having received a resounding clap from the assembled folks. And before we go, I would just like to say that the next session we're going to have is on June 10th. We're going to have Hatch Space with Tom Bodette. And this is a Tom Bodette that you're used to hearing either on Wait, Wait, Don't Tell Me, or the guy who talks about leaving the light on for Motel 6. But he won't say that outside of those commercials. So don't ask him about that. But anyway, Tom will be talking about Hatch Space. It's a program that he started, a space that he's created with a number of other people up in Vermont, and it should be a really interesting talk. And I think it suggests to us, the guild, members of the guild, where we'll be going. And then we'll be talking on the 24th about the apprenticeship training program. It's just going to be pretty much an open discussion, and that should be of significant interest from many of the folks. And we're going to be looking for support and help from the members and what they think we should be doing with an apprenticeship training program on June 24th. I also want to take this opportunity, speaking to everybody here who's interested in engineering, that on July 22nd, Dick Schmidt is going to be talking about measuring knots. His subtitle there is, "They are smaller than you think." In other words, this is something that timber framers who are using #2 and better material oftentimes, and they're judging the size of their knots. There's an opportunity for you to perhaps use your material a little bit more efficiently. So I don't want you to think that that's going to be a really uninteresting night with Dick Schmidt. I think it's going to be very interesting and actually very cost-effective time for you to understand exactly how the knots are going to be measured and therefore be able to use your material more efficiently. So, unless somebody else has final comments, we'll call it good.
I want to say thank you to everybody who took the time to listen, and thank you, Janet, for all your support in this. And I'll see you all later.
Cool.
Thank you, Mac.
Good night, everybody.
Bye.